Hi everyone, my name is Wilson and I'm here to present our work from explanation to feature selection, assessing SHAP values as feature selection mechanism. Here's the outline of my presentation. Working with high-dimensional datasets has become one of the essential aspects of working in academia and job market. However, these datasets present some issues regarding redundancy, which impairs existing technique. The redundancy can be decreased by using dimensionality reduction techniques or feature selection techniques. And when we are deriving a machine learning solution focusing on interpretation, it would be interesting to have explainability in all aspects of the pipeline. For example, for feature selection. And however, the existing feature selection techniques show some explainability issues. For example, we have three classes of feature selection methods: the filter ones, the wrapper ones, and the embedded ones. The filter ones do not leverage models' characteristics, so we can use it to interpret a machine learning solution with it. The rapid ones are based only on a scoring performance, and we cannot derive an interpretation of a machine learning model using only the scoring performance. And the embedded ones have been incorporated in each model that is being analyzed, which is a feasible solution since we have a lot of machine learning models. In this case, our contribution lies on providing feature selection mechanisms using SHAP values. The SHAP values is a model agnostic explainability approach which uncovers the feature's contribution to a model's prediction. In this case, we use these contributions to a measure of importance to then use it to select a few features from the data sets. And by comparing this approach with well-known feature selection algorithms, we could notice that SHAP values present the best result according to feature importance for a metric that we used. The little background, as the SHAP values is a model agnostic additive explainability approach in which each prediction of a model is explained by the contributions of the features. For example, here we have the output of a model, 24.41, and we have the contributions of each feature to the predictions, right? And we have the positive contributions and the negative contributions. And if we sum these contributions, the positive ones and the negative ones, we could, the positive ones, sorry, and the negative ones, we will have the same result as the model output. Okay? So in this case, we have the greatest SHAP value for age. Our methodology works as follows. For a classification problem, we'll have a number of matrices as the number of classes. Here I have 3 classes. And for each class, I derive a matrix It's the size, the dimensions of the data set, of the text data set, for example, and each cell of this matrix corresponds to a SHAP value. To compute the mean of contributions, take the mean of the columns for each matrix that corresponds to each class, like in this process here. Okay, and this mean is computed by taking the absolute value of each cell. Then we sum these resulting vectors to derive a vector that corresponds to the importance of each feature. In this case, here I have the importance in blue and the absolute SHAP value in red. Okay. As we can see here, I have the most important feature as the second feature, the second most important feature as the third feature, and so on. We evaluated SHAP values as feature selection with three common feature selection approaches: recursive feature elimination, mutual information, and ANOVA. And we tested according to classification and regression tasks using the XGBoost classifier and regressor. We grid searched for the best parameters for each dataset, 5 datasets for classification tasks, and 3 datasets for regression tasks. And here I have the parameters with alpha as the learning rate, beta as the maximum depth, and the number of estimators, right? And I have the corresponding parameters indicated in here. To evaluate, we use the keep absolute metric, which works as follows. First, we have to fix features for classification. These features correspond to the most important features. For example, in the first step, I fix only the F1 feature. In the second step, I mask the other features. By mask, I assign the mean value of each column to each corresponding cell. For example, if I want to mask the feature F3, I assign to each cell of F3 the mean of this particular column. Then I feed into the model and compute the scoring value. In this case, we use accuracy for the classification tasks. And I keep increasing the number of features kept for classification to produce a curve like this, right? Here I have the results for classification tests. We can see that 3SHAP yield the best results among all the techniques. And as well for regression tasks, the 3SHAP produced the best result for 2 datasets, and the second best result for the Boston dataset. And if we look at the results, the difference is really small, right? And here I have negative values because we use a library to compute the best results, and the library use negative value to maximize a result and produce negative values. Okay. The time execution is the main drawback for the SHAP values. As we can see here, it corresponds to the second worst technique in terms of time execution, runtime execution. Here, as of for regression tasks. And finally, we have some discussion about our work. First, we know that SHAP value has been used to discover patterns and help interpreting models in earlier works. And feature selection, which is a widely preprocessing step in machine learning solution, can benefit from those explainability characteristics. So we can extrapolate the concept of contribution, feature contribution, to feature selection, as we could see in this presentation, enhancing interpretability aspects of in all of these steps, developing steps of machine learning solutions. Okay. However, the main drawback of such approach using SHAP values as feature selection is the computational complexity of the model agnostic approach, such as kernel SHAP, since SHAP has a lot of implementations for each model. Concluding our presentation, we know that model explainability has been one of the main issues in current machine learning approaches. And however, there is little discussion regarding the explainability aspects in machine learning preprocessing steps. And in this work, we present a strategy for feature selection with an existing technique, SHAP values, for selecting features according to their contribution to a model's prediction. And in future works, we plan to analyze it in detail by considering the ordering of the features returned by SHAP and other feature selection techniques. We'd like to thank CAPES and FAPESP for the funding. And thank you very much.